So welcome to the 63rd Theoretical Physics Colloquium by Dr. Yacine Mehtar-Tani from Brookhaven National Laboratory. He got his PhD in 2006 from Theoretical Physics Lab in Orsay. After that, he had several postdoctoral positions. He spent about a year at ECT STAR in Trento in 2007, then moved on to a postdoctoral position in Heidelberg at the Institute for Theoretical Physics, where he spent 2 years. Then he was for a year at Santiago de Compostela in Spain, and then moved on to the Theoretical Physics Lab in Saclay in 2011. In 2014, he became a research assistant professor at Institute for Nuclear Theory at the University of Washington and became an associate scientist at Brookhaven in 2018. Since 2020, he is a RHIC and Fellow at Brookhaven, and since fall, he became the scientist at Brookhaven National Laboratory. He is serving as an appointed member of the RHIC AGS Users Executive Committee. His research interests include QCD, jet physics, physics of heavy ion collisions, jet suppression in heavy ion collisions, and many other things, deep and elastic scattering. And today he will be talking about wave turbulence and anomalous diffusion of jets in the QGP. And with that, I'll give the microphone to Yacine.
Yeah, thank you, Igor, for the introduction and for the invitation. I'm pleased to be here and talk about some recent work and some general ideas that occupied me in the past few years. So we'll talk about new aspects of high energy and high density QCD that emerge when jets traverse dense deconfined matter, quarks and gluons. So those emergent phenomena, well, of course, there are many of them, and I will focus on interesting aspects related to wave turbulence and anomalous diffusion, which were recently understood. So before talking about jets in heavy ion collisions or jets in QCD matter, let me first introduce jets in vacuum. So QCD jets are described by collimated sprays of particles, and they are observed in high energy collisions. As you can see here, you have this event display of back-to-back dijet event, where you see a bunch of particles. So this is what's measured on detectors. You measure hadrons, and they are quite collimated, and this is what is called the jet. So this is a dijet event from the CMS collaboration in proton-proton collisions. And you can see here, this is almost half a TeV jet energy, and the energy is quite balanced because of energy momentum conservation. So this is a jet for what you see from the detector. So jets were predicted a long time ago, the late 70s, as being dominant in the cross-section plus and minus. You can also use jets to probe QCD, and here this was after the dijet event prediction observation came the observation of the 3-jet event as probably the most direct evidence of the existence of a gluon. So this was somehow rather fantastic measurement by the TASO collaboration, where you can see here this called Mercedes-Benz event here. It has this 3-jet event where one of the bunches of particles here, in fact, is a gluon. So we are in fact staring at a gluon, if you will. So this is quite a remarkable test of QCD. So this was for decades, 4 decades ago. So nowadays, we study jets as precision tools to probe QCD. This is one of the aspects of studying jets. So as you can see here, jets are used here for the measurements of the strong coupling constant by the CMS collaboration here. These are the solid circles here. Many observables to a certain degree of accuracy. This is the inclusive jet spectrum, just to quote one of them, measured here again by the CMS collaboration compared to theoretical predictions that are included in this event generators called POE, to next to leading order accuracy. So also recently, there's a growing effort to study jet substructure going into more details in the substructure of jets and study more QCD dynamics at the partonic level, and use that also for the search of new physics. So jets also played a very important role in the Higgs discovery. So as you can see here, this is Higgs decay into a BB bar pair at the LHC, and jets are essential to dig out the signal, the Higgs signal here, as jets constitute a large part of the background. So it's very important to know how to calculate jet cross sections to a high degree of precision to be able to measure this the small Higgs signal, and of course for beyond standard model searches as well. So this is, as I said, jets in vacuum. But what is a jet, in fact? So I said a jet is a bunch of collimated particles that are measured at the depth. These are hadrons. But in fact, the way we see jets from QCD standpoint is rather somehow reflect accurately the physics that's the dominant physics, so to speak, because there are two stages in jet evolution. So jet is born from a high energy parton. This is a gluon that is produced in a high energy collision, but then this gluon will undergo a branching process. And this branching process, although it is suppressed by the coupling constant alpha s, it is enhanced by large phase space, logarithmic phase space. So we have a collinear singularity. This is standard mass singularity in gauge theories, and a soft singularity. So the collinear singularity is the reason why we see collimation in jets. But of course, at the end of the evolution, this partonic regime, hadronization takes place after a degradation of virtuality. So in virtuality, initial virtuality, which is of the order of the jet energy, goes down to lambda QCD, where hadronization takes place and partons are converted into hadrons. So the phase space, or let's say the time span of this partonic evolution, is rather large. And the higher the PT, the larger this partonic evolution window. And in between the, say, the initial time for the hard process all the way down to hadronization time, the evolution is self-similar. So the same process repeats itself. So it's the 1 to 2 branching process. And this self-similarity is well described by this simple probability emission. So there is more to the definition of jets than simply having this cascading process. You still need to define a jet from an operational perspective. So what is a jet? So we need to confine a jet inside a certain cone of size R, which means that there is not a unique definition of a jet. We also need to figure out how to cluster the final particles in a certain way so that we can trace back the original parton. And there are many algorithms, and this introduces a certain ambiguity in how we define jets. But to a first approximation, jets is rather qualitatively well-defined object besides those small operational differences here. So as I said, there's a large phase space for partonic shower, and hadronization is of course modeled for certain observables, but for a large part of observables, which are called infrared collinear safe observables, like the inclusive jet spectrum, the physics at the hadronization scale is power suppressed. So most of those observables are in fact mostly sensitive to short distance physics, which is this partonic stage here. So this is a jet. Oh, a last point here. In addition to this collinear and soft singularities, there is the phenomenon of so-called color coherence, which imposes radiations, successive radiations, to be ordered in angle. And the physics behind that is also, in fact, common also to QED, which says that soft radiation of multiple legs will be suppressed at large angles simply because the transverse wavelength of the radiated gluon won't resolve the inner structure of the jet, and hence it has to be suppressed as it will be sensitive only to the total charge. So only radiations that are collinear and close to the emitter will be somehow enhanced. Large angle radiation will be suppressed by destructive interferences. So now let's move to jets in heavy ion collisions. So this evolution, this cascade evolves after the particle is produced. This evolution happens in vacuum. So this is somehow a coherent quantum system, and color, energy are conserved throughout this evolution process. This is no longer going to be the case in heavy ion collisions, where a jet won't conserve its energy. It will lose energy to the to whatever medium it's propagating through. It will also suffer color randomization. So if it interacts with, of course, it's going to interact with a colored medium, it will exchange rapidly color, and this will randomize the color. So all of those phenomena somehow will trigger new processes that I will discuss soon. So what is the overarching somehow question here? So we study QCD also to probe the proton structure, and I mentioned also new physics and jets and precision test of QCD. This is probed in small systems. These are small systems here. Few particles produced in the found states. Although at high energy, we measure a lot of particles, but typically a much smaller number of particles than in heavy ion collisions. We study ultra-relativistic heavy ion collisions for many reasons. So there are, of course, many questions that I won't touch into here in this talk. But the basic idea is we want to study, we want to be able to probe using an experimental setting, which is heavy ion collisions, to probe the QCD phase diagram. But to get to that somehow question, we need to first go through understanding how we go from zero temperature to final temperature through, I have to go through understanding non-equilibrium dynamics of QCD. And this is what involves collectivity, jet quenching, quark-gluon dissociation. So a lot of questions that are akin to transport process properties of QCD that span, in fact, a very large window of scales, going from the TV to the GV scale. So you can see here the comparison between a dijet event in nucleus-nucleus collisions, where the dijet here event is embedded in a very large background of particles. Thousands of particles are produced here compared to order of magnitude lower number of particles produced in proton-proton collisions. So we need to understand how to couple QCD or how to enhance our quantum field theory to account for a large number of degrees of freedom, and this would involve including statistical physics techniques. So what happens in heavy ion collisions? So-called little bang. So a heavy ion collision starts with, of course, colliding two pancakes. These are two heavy nuclei that are Lorentz contracted. Right before the collision, they look like this. And after the collision, a large number of particles of gluons will be produced, right? And this large number of gluons will start interacting strongly. And eventually, after a certain time, this would lead to hopefully just approach to equilibrium and then thermalization, and hydrodynamic behavior would set in. So the main, before even talking about hydrodynamization or thermalization, the most important message here is to say that there is a deconfined matter of gluons and quarks that leave over extended period of time that enough to be probed in experiments. And this is the so-called quark-gluon plasma. So there is a transition into this deconfined phase transition from hadronic degrees of freedom to partonic and quark and color degrees of freedom. So many phenomena would appear, and this is what we would like to study with heavy ion collisions. So we have plasma instabilities, turbulence, and at the end of hopefully at the end of this kind of non-equilibrium dynamics, we approach a certain thermal equilibrium, or more accurately, as we believe today, hydrodynamical behavior. So the QGP is studied by studying the measuring bulk observables, typically particles of the order of a GeV, and one of the most remarkable features is the fact that this matter that's produced behaves like almost a perfect liquid. So there is a collective behavior which is measured through the flow harmonics, and those flow harmonics simply express the response of the system to the initial geometry. So this initial geometry, which would just the spatial anisotropy, would transform and translate into a momentum anisotropy after this strong interaction in the found state. And those flow harmonics are what described by viscous hydrodynamics with a rather low viscosity. And this viscosity to entropy ratio is very close to a lower bound that was found in ADS-CFT correspondence by Polycastro, Son, and Starinets in 2001. So this simply says that the QGP is rather almost ideal fluid, and it's rather well described by hydrodynamics. But then, of course, this matter, this regime of heavy ion collisions is in the low end of the spectrum. So we're talking about up to a few GeV, and this is well described by hydrodynamics. But in the particle produced in the final state span a much larger, say, window of scales, all the way to a TeV at the LHC, and at RHIC it's going to be a few tens of GeVs. And the question is, what happens in between? And this is where jets come in. So a bit of history. So Bjorken in 1982 predicted the phenomenon of jet quenching. So basically he said that if a jet goes through or high energy quark-gluon propagates through quark-gluon plasma, it will suffer energy loss. Of course, he had in mind elastic energy loss. We know today that inelastic processes are also very important in making jets lose energy to the plasma. So he predicted that the cross section would be suppressed due to energy loss. So this phenomenon was measured at RHIC through this emblematic observable called the nuclear modification factor, which is basically the ratio of the yield of hadrons or jets in nucleus-nucleus collisions, and the yield to the ratio of the yield of the say the particles in AA to the yield in PP. Sorry, this is not, there's a typo here. It's going to be PP normalized to the number of binary collisions. So in the absence of any final state interactions, this ratio is expected to be 1. So if you had no final state interactions, neglecting also any nuclear initial state nuclear effects, this ratio would be 1. So any departure from 1, as you can see here, 1 is here, strong suppression would indicate very strong final state interactions. And this is what we see here. So you see here in the production of high energy hadrons all the way to 20 GeV, you see strong suppression of particles in at RHIC. And also jets. So jets were also measured at the LHC and also measured at RHIC recently. But here you can see all the way, so there's a strong suppression of jets. So the RA is around 0.5 all the way to 1 TeV. So again, this indicates a strong final state interactions. So as you can see, so what happens, this is a sketch of what happens in heavy ion collisions. So this is a divergent event produced in PP collisions. Jets are produced right after they're produced, they evolve in vacuum completely independently, and they fly into the detectors. Here, of course, they have to pass through this colored dense medium of quarks and gluons, and the strong interactions in the found state will be responsible for the depletion of jets observed in the data here. So the question is, what are the mechanisms responsible for this suppression? So this is just to show this dijet event from CMS, where you clearly see, as I said in the beginning, because of energy momentum conservation in PP collisions, we expect a perfect, almost perfect balance of momentum dijet event, which we don't see in heavy ion collisions, simply because one of the jets will make it through a larger portion or extent of the medium and lose more energy, and you end up having more events with imbalanced momentum of dijets. All right, so why study jets in heavy ion collisions? I already alluded to this in the earlier, but what are the typical questions that we would like to address? And what we have learned trying to tackle these questions in the recent years. So of course we want to study jets to probe the quark-gluon plasma. So this is a hard probe. The jet would go through the plasma, and any modification that the jet would suffer as a suppression or broadening or distortion, any modification would tell us about the nature of the plasma the jet is interacting with. So this is in some sense complementary to bulk observables, and this would allow us to also have another somehow access to properties beyond the typical scales that are probed by flow harmonics, like, as I said, the GV scale. So this would allow us to probe higher, larger range of scales to of the quark-gluon plasma. So those jet modifications will allow us also to probe the non-equilibrium dynamics of QC. So typically, when a jet goes through a plasma, it would tend to lose energy until, if the plasma extent was infinite, the jet eventually would thermalize, would simply melt into the plasma, would lose energy until all of the particles would thermalize. And this, by studying jets at the various ranges in PT, we would learn about how thermalization occur in practice and in experiment. So the main question is how energy is then transported from hard jet modes of 10 to the 100 to the TV scale down to the temperature scale, which is less than a GV scale. Well, this was studied and understood from a weak coupling perspective, and it's called the bottom-up scenario. It involves many processes, including elastic and inelastic processes, and jet may help to understand the details of this thermalization process. So of course, will allow us also to investigate transport properties of QCD matter, as I said, at different scales, and I will touch on this recent discovered phenomenon, which is the anomalous diffusion of jets in QCD in the quark-gluon plasma. More generally, you can view jets as jets embedded in the quark-gluon plasma as an open quantum system. So jets are in contact, as a quantum system in contact with a reservoir, and which would tend to destroy its quantum coherence and would randomize its color. So there are many questions. Of course, I'm leaving out many other interesting questions. But the main message here is that jet will allow, in fact, to scan the plasma properties over various range of scales. So as I said, QGP is a perfect liquid. There's evidence of that, and which points to a strongly interacting plasma. So if the plasma is strongly interacting, and if jets are weakly interacting partonic systems, so we know how to compute jet observables from first principles using perturbative QCD. So we need the coupling to be small, and we know that jets are well and precisely described by perturbative QCD, recoupling. How can we understand then the interaction of a weakly coupled object, which are jets, with a strongly coupled QGP? How does this interaction happen? Most of the theory work is based on assuming that the plasma is weakly coupled, but this question is more general. So can we figure out a way similar to deep inelastic scattering, where we have a certain renormalization group equations that allow us to connect the long distance physics, which involves confining forces and so on, and the short distance physics, which is calculable, and the matching to that is given by renormalization group equations. So this is still one of the questions that we would like to tackle here, and along the way we might understand how QCD behaves in this type of phenomena, in this type of processes. So this is a sketch of what to expect. So again, this is our jet here, cascade. This is the standard collinear branching process that happens in vacuum in the absence of the medium. And then, of course, the interaction with the medium would trigger additional radiations and multiple scatterings. So the jet partons would rescatter, suffer multiple scatterings in the plasma, and also induce medium radiation, which again trigger a parton cascade that goes to large angle that will be responsible to taking away energy from the leading partons down to the temperature scale where thermalization happened. So as I said here, we have almost 3 decades, 3 order of magnitudes here of scales here, and starting from the jet energy, the PT, and then this is just the virtuality, typically the virtuality of the jet, then the mass of the jet. These are all properties of jets in vacuum. And then when we go down the GV, the PT scale here, we start encountering medium scales. So the first scale we encounter is related to transverse momentum broadening, which is what happens when multiple scatterings here transfer some transverse momentum to the jet, and this would lead to its transverse momentum broadening. Then, of course, all the way down to the temperature where dissipation effects happen. So the question again is, how is energy transported from the TV scale down to the GV scale? So this is a multi-scale problem, and we need to understand how perturbative physics, which is expected to, which we know takes place, is applicable here at high scales, can be coupled to non-perturbative regimes where maybe holography or other techniques may be used, but we would like to be able to have a comprehensive description where which doesn't depend necessarily on the detailed properties of the physics around the GV scale here, or below. So as I said, we have possibly 2 regimes. We could have just a weakly weak coupling regime. We could imagine a plasma which is weakly coupled if the coupling constant is small, and then we can have a complete description in terms of weak coupling. But in general, we could think of really the problem into divided into 2 pieces. We have the weak coupling regime, as I just said, which is calculable under analytic control. We can estimate the theory uncertainties. There are summations to be performed, so we need to resum a certain class of diagrams, but this is somehow, we may devise a systematic approach to calculate observables in this regime. But then we have non-perturbative regimes. Already in vacuum, we need to deal with hadronization, and in the medium, we need to of course, involve be able to understand dissipation, hydrodynamic behavior, can use kinetic theory. So this is probably the realm of modeling, because we want to probe the plasma, which is somehow producing heavy ion collisions. And in this regime, if the coupling is large, then we'll have to resort to a certain degree of modeling here. But the question is, can we still probe to a certain accuracy the plasma using hard probes? And the answer is yes, because we have this large separation of scales where for certain observables, of course, similar to the infrared collinear safe observables in vacuum, which are not sensitive to hadronization, there would be some observables that will be only sensitive to medium properties through transport coefficients, which I will come back to later throughout those, like the quenching parameter Q hat and E hat, which encapsulate the medium properties and enter the calculation in the weak coupling regime as parameters to be fitted to data. All right, so what are the different processes that I will discuss here? So as I said, there is a medium-induced turbulent cascade that is triggered by multiple scatterings that I will discuss here, and the how normal diffusion that happens when we restrict our description to leading order turns into super diffusion process when we account for quantum corrections and resummation of higher order corrections. So there are the two bullet points that I will discuss. There are other phenomena like color decoherence that results from the fact that a multi-partonic system may lose energy as a single color charge due to destructive interference, which I will not cover in this talk. So turbulent energy loss. So let me just say a few words about turbulence before I go into some very general considerations about turbulence. So the most remarkable theoretical result related to turbulence, classical turbulence, was given by Kolmogorov and Obukov in 41, where they try to understand how turbulence would set in, how to understand it. So basically, turbulence is any phenomenon where by exciting a certain fluid, it would generate eddies that would break into smaller eddies and so on until reaching a certain scale from the injection scale to a dissipation scale here. So the assumption of Kolmogorov was to say, well, in this range called the inertial range, there is local interactions and self-similar behavior where the physics can be described only through the energy flux epsilon and the wave number k. And using dimensional analysis, they got this power spectrum, this famous 3/5 power spectrum for the energy correlator. And so this is a very simple result, which is rather important because it states that the physics in this inertial range is not sensitive to what happens at the injection scale, the large scales, and then of course to the not sensitive to the dissipation scale in the other end of this cascade here. So in other words, even if the dissipation was put to zero, the cascade wouldn't know it and would continue simply branch, and you still get smaller and smaller eddies forever. So this is basically the locality of interactions. So this is the self-similar behavior was the breakthrough here. So there are other processes now that exhibit similar behaviors, similar scale invariance, which are related to nonlinear wave systems. And there are many of them, like atmospheric waves, water surface waves, waves in plasmas, and also observed in nonlinear optics. So there are many physics processes that exhibit wave turbulence, which have also similar self-similar and scale invariance property. So again, the similarity with the fluid turbulence is this inviscid transport of conserved quantities from large scales to small scales through this so-called transparity window. And this is what we will observe in the transport of energy from jets to the quark-gluon plasma. So what are the elementary processes? I already mentioned the momentum broadening. So multiple scatterings here may transfer transverse momentum to the jet particles, and this is described by this diffusion coefficient called Q hat, which is simply a measure of the transverse momentum squared per unit length transferred to the jet here. Multiple scatterings also trigger soft radiation, and the medium-induced radiative rate is, of course, suppressed by the coupling constant, but scales like 1 over square root of the frequency of the gluon, the radiated gluon, and this square root omega is a reflection of the QCD analog of the LPM effect. So these are the two processes, elastic processes and inelastic processes. And before going into discussing the cascade, because those are the two processes that will trigger the cascade, the turbulent cascade I will discuss, let me just say a few words here about what the quenching parameter is. So at leading order, we can compute this quenching parameter, say in the thermal medium. And the leading order diagram is just this 2-2-2 matrix element in the high energy limit, where the momentum exchange is much smaller than the square root of S. And the cross-section scale is like 1/QT⁴, which is the standard Coulomb scaling. So the cross-section goes like 1/QT⁴. If we are interested in the average KT squared, so we have to weight it by the by QT squared, and integrating this, we get a logarithmic enhancement here, which is the standard Coulomb logarithm, also observed in QED, proportional to the density of scattering centers, which is T⁵, and then of course the coupling constant G⁴, which is simply the square of this process here. So this is the leading order result for Q hat. And fitting Q hat to the data would mean also fitting the temperature or the coupling constant here. We have also an operator definition, which is non-perturbative. As I mentioned before, Q hat, if the medium is non-perturbative, we will actually have a non-perturbative definition. And to some extent, Q hat is related to the gluon distribution, the gluon PDF of the medium, measured at the Bjorken X fraction equals to 0. This is just this given by this 2-point correlation function of the field strength tensors in the medium. So the Q hat encodes local and global medium properties, as I said. So it's also sensitive to the coupling to the medium, and also might also be sensitive to some UV scale here through this logarithmic, the Coulomb logarithm, and also to the size of the medium. And this will appear also later when I discuss this the anomalous diffusion. So multiple scatterings may trigger coherently radiation, and this would take place over a time, formation time TF, this quantum mechanical formation time TF, which goes like ω/kT squared. During this formation time, this quantum mechanical formation time, the gluon would acquire transverse momentum using this formula, diffusion formula, which is Q hat times TF, and by solving this for TF here, these two equations, we get that TF is scaling like square root of ω/Q hat. And this is a result of the multiple scatterings that act as a single coherent single scattering during that formation time. This is how we get the LPM suppression in the UV by simply multiplying, of course, the formation time times the length of the medium, because this could happen, this process could happen anywhere along the medium, so it scales like the length, and the other scale in the problem is this formation time, so it has to go like L over the formation time, and hence the spectrum scales like 1/√of omega. So this is the microscopic process, which will reflect itself macroscopically in the turbulent cascade. So again, the spectrum goes like 1/√of omega. And the LPM suppression is simply saying that because of the coherent involvement of scattering centers here, the spectrum is suppressed compared to incoherent, the Bitter-Heitler regime, which is the incoherent sum of scattering centers. So we obtain a characteristic frequency. Again, this is maximum characteristic frequency that can be reached by the spectrum, above which the spectrum is even more suppressed. This is ω/c, which is simply Q hat times L squared. There's also a minimum angle for this process to happen, which is this characteristic angle θ c 1/√Q L cubed, which shows clearly that the medium-induced radiation happens at large angle, and there is no collinear singularity as in vacuum jets. So this is the elementary process for radiation. This is the leading order. And this process could have, as I showed here, the rate for this process is enhanced for soft radiation. And this, when omega goes to 0, the probability for radiating more and more gluons is very large, and we have to resum multiple radiation. And this is what happens here. So we end up having a rate equation, a kinetic description for multiple branchings. Each branching, of course, is triggered by multiple scatterings over time, formation time TF, which scales like square root of omega. And then multiple scatterings and multiple emissions happen between two. Typically, the branching rate is given by 1 over alpha TF. And as you can see, the two splittings are well separated, since the radiation time is TF and the time between two branchings is enhanced by 1 over alpha S. So we have a kinetic description that is given by this rate equation for the inclusive distribution of partons here in the final state. Z is the fraction of the final parton, the energy fraction of the final parton measured here, and Kz is just the splitting function. It's just how energy is shared by the daughter partons here. T star here again is the branching rate, and it will encompass this square root of x scaling of the LPM spectrum. So now we can solve this equation, and what we observe is this. So if we start with an initial condition where all of the energy is carried by a single parton, so for x equals 1 here, x being the energy fraction, so x equals 1, we have a single parton, it's a delta function. After some time, we start radiating gluons, soft gluons, according to this spectrum, leading order spectrum, 1 over square root of x. This is the first time, and then second time it goes up. More and more gluons are radiated, so the process will somehow scale with the length of with time. So this goes up. Then after some time, nonlinear effects become important. More and more branchings are somehow produced, and then energy is depleted from the jet here, from the leading parton, and starts flowing with constant rate throughout scales all the way down to the temperature scale. Here there is no temperature, it's 0. So you end up getting here a rather steady state here, 1 over square root of x at all times, as you can see. So this 1 over square root of x is in fact associated with a constant flux of energy, and this is akin to wave turbulence, to this Kz spectrum. And the reason why this is sustained is again due to locality of interaction. This is again related to wave turbulence. So branchings that happened in this inertia range are not sensitive to the physics around the injection scale here, or the physics of dissipation. So this is these locality of interactions, which leads to this self-similar branching process and the sustainment of this 1 over square root of x. So energy doesn't accumulate in this inertia range. You get simply this 1 over square root of x. There is a characteristic frequency for thermalization. If the jet energy is of order of this scale omega s, then the jet would completely lose its energy to the plasma. So this gives us a stopping distance after time 1 over alpha square root E over Q hat, E being the energy of the jet. After this time, the jet is completely thermalized into the plasma. The other characteristic quantity due to the multiple branchings are the large angle cascade. And again, you get here this 1 over square root Q hat L cubed, not squared, but then you have an additional enhancement factor 1 over alpha squared. If alpha is small, this is the coupling constant, you get a large angle for this cascade to take place. So now we can solve numerically the coupled equations for quarks and gluons and see whether, in fact, we see persistence of this Kolmogorov-Zakharov scaling. And in fact, this is what we see. So we see that for different times, the jet starts here at 1 and then starts depleting its energy. But then during this evolution, the Kz spectrum X 1 over square root x. Here it's multiplied by, the distribution is multiplied by square root of x, so that this would correspond to a flat distribution. So it's really persisting over time. And this is again simply indication of a constant flux of energy from the large scales to the temperature scale here. So what happens now if we account for dissipation? And this is probably how we could appreciate the locality of interactions during this inertial range. So by coupling, having a full kinetic description where dissipation processes are accounted for, nonlinear effects around the temperature and detailed balance is accounted for. You see that again, we see the same picture here, the jet at 1 depletes its energy, and then you have a regime of cascade, and you see here again this flat behavior, which simply translates the 1 over square root of x turbulent scaling. And then only when we approach the temperature scale do we see thermalization or dissipation processes. And this distribution is simply the thermal distribution. So partons that reach temperature scale starts interacting with the plasma and simply thermalize. So you can see here clearly that even thanks to this large separation of scales, kinetic theory predicts such a 3-stage process here. So there are other universal features to this cascade, and one of them is the chemistry or of the cascade. So we have studied the ratio quark-gluons, and then we can see that this ratio is universal. Is not again sensitive. When I say universal, it's not sensitive to the physics as the injection scale, nor at the dissipation scale. So this ratio of gluons to quarks is only sensitive to the integral over the splitting function in medium splitting function here for the gluon going to the gluon to quark and quark to gluon. And this is remarkable. This tells us that the microscopic physics, the microscopic elementary processes, which are the 1 to 2 processes that are responsible for underlying the cascade, can be seen in such a ratio at the microscopic level. So this is interesting. This somehow, again, another translation of the self-similarity. So the physics at the given scale will show up at larger scales here. So the numerical simulation shows similar behavior. Of course, here close to the injection scale, you see large departures here at different times. So here you see again different times, but at low, when you move away from the injection scale, which is at 1, at very low energy fraction x, all of the curves, they tend to this universal ratio here, which is predicted theoretically. So this is numerics, and this is the theoretical prediction. Of course, when we get again closer to the dissipation scale, we should see departures. In the simulation here, there is no dissipation, but you see still, if the window is wide enough, we should be able to see this universal ratio. It would be interesting to investigate this from an experiment. So again, just to repeat what I just said, we have 3 stages. We have the injection scale where jet modes leave. This is the collinear jet modes. And then energy is transported from the jet scales throughout a local turbulent cascade that will take energy down to the temperature scale where thermalization happened and particles stem. So, and in this regime here, this inertial range, physics is completely local and independent and universal. And this of course happens so long as we have this wide range of scales to begin with. So this comforts my initial somehow point that the physics of around the jet scale and of course the physics of energy transport will not be sensitive to the details of thermalization and can only, and somehow is sensitive to the physics of the medium through transport coefficient Q hat. So Let me move to the last, second and last part of my talk, which is the anomalous diffusion. So the probability distribution for a high energy particle to acquire transverse momentum KT, especially in the bulk of the bulk of the probability distribution, is given by Fokker-Planck equation, where Q hat is the diffusion coefficient. So from just this equation, we know that normal diffusion would lead to the first moment of the distribution scale linearly with time. So this is standard normal diffusion. And the question I would like to ask here is, this is the leading order calculation where only the 222 matrix element is accounted for here. So the jet particle here is interacting with one particle. This is G to the fourth. This is 222 matrix element. This is what I call leading order. Of course, it's resum because of multiple scatterings, but it's leading order. This leads to the normal diffusion. And the question is, do quantum corrections alter the classical picture that we established here? All right, so tree level, this is leading order. So leading order, this is what we get. We get, of course, naturally, we would do the calculation in coordinate space, where we can exponentiate the 222 matrix element, and then take the Fourier transform. But the point is, solving for this with Q hat leading order simply proportional to the Coulomb logarithm will have two regimes. So one regime is just the Gaussian distribution, which is solution to the Fokker-Planck equation. We get Gaussian here, and then the transverse momentum squared is simply proportional to the Q hat times L. So that's typical transverse momentum squared that gives this peak region here. At large transverse momenta, the distribution falls like 1 over kT to the fourth, which again reflects the 222 matrix element with the tail, which is 1 over kT to the fourth, the standard Coulomb tail. So this is the leading order. How does this change when we compute high order corrections? So high order, of course, comes with an additional factor of the coupling constant alpha s. But what happens here is that an additional radiation, even if it's suppressed by alpha s, it is enhanced by a potentially large logarithm, because the phase space for this radiation, which is in fact non-local, this radiation can somehow extend all the way to the boundaries of the medium. So it's a non-local process, and it leads to this to the double logarithm of the length of the medium divided by medium scale here, which is related to the Debye mass, which is assumed to be small. So we have large logarithms which need to be resummed, and the resummation, the all-order resummation of those logarithms can be accounted for through this evolution equation for Q hat. Very similar to D-Glap evolution equations for Parton distribution functions. The difference here is that this evolution equation resums double logs that account for only single scattering here. So the double log lives in a region where only a single scattering happens. But we have multiple scatterings. So the multiple scatterings will provide a boundary, will tell us where the double log lives. If the double log would be limited by the region when multiple scattering become important. This happens typically when the transverse momentum is below a certain transverse momentum scale given by the medium, which is this saturation line. So below this line, when KT is below this line here, multiple scattering become important and the double log is suppressed. This is reminiscent to the physics of color glass condensate, where nonlinear effects in the at high energy nonlinear gluon emergings leads to the emergence of this of a new scale in the proton structure. Okay, so now we can resum those double logs, and just to show that indeed this is related to the gluon PDF, we can resum and to leading order just by expanding the exponential. This is the rare events where you have just one scattering. So you have one scattering, but still you have kind of an evolution from the jet KT down to the Debye mass. And then you get the 1 over KT to the fourth, but all higher orders are encoded in the evolution of Q hat. And to the asymptotic behavior, when KT is very large and L is very large, is simply standard double logarithmic approximation in QCD. So just an exponential of the square root of the log of KT over the Debye mass, and then the log of the length of the medium. Again, this is what you expect if you compute the double logarithmic behavior of the gluon distribution at x equals to 0. So this is a leading log result. Nonlinear effects would change this picture. So they're nonlinear because of the existence of such a scale, this QS scale. We can show that there are exact solutions, exact scaling solutions when the length of the medium is large, and that's an important observation. So we can, by assuming a scaling solution for Q hat, Q hat is a function of KT and L, but if we assume that Q hat is simply proportional to this saturation scale, which is just a function of L times a scaling function of X, which is KT over QS squared, we can show that the equation, the evolution equation for Q hat, which is this equation, admits scaling solutions of this scaling variable X, again, which is transverse momentum over QS squared. So the dependence on the length of the medium is appears only through the saturation scale here. So the details of the form of this function, scaling function, are not very important. Probably the important point here is the appearance of this anomalous dimension beta here, which is the square root of alpha bar. The numerical simulation, given a certain initial condition for different values of the length of the medium from 10 Fermi to 500 Fermi, you can see from the red curve, this is the time evolution, from the red curve to the green curve here, the evolution towards the exact analytic solution, which is given by this scaling formula. So there is somehow convergence to this asymptotic solution here for Q hat, confirmed by the numerics. So now the scaling for QS, this saturation scale, which is related again to the transverse momentum broadening scale, at leading order it scales like L, the length of the medium, that's normal diffusion. But because of the high order corrections, which are result to all orders, we get an additional shift of the power of the scaling here by 2 square root of alpha bar. This leads to anomalous diffusion, and in fact, because the power is positive, it's called super diffusion because it tends to diffuse rapidly in the medium. And again, this is related to the non-locality of quantum corrections. So what happens at the level of the distribution itself? So now PKT. So we're going back here. We go back to this tree level. So we had the Gaussian, and then we have the 1 over KT to the 4. What happens now? Well, this is what we get. And then I plotted it here as a function of X again. You see all of the curves for different L's, all the QS changes with L. So QS increases with L, as I said, it's L to some power. All of the curves, when plotted as a function of X, they go on top of each other. So this is somehow geometric scaling, which extends all the way to very large KTs. This is quite remarkable. So as I said, this is a super diffusive process, which exhibits scale invariance, which is akin to Levy flights. So Levy flights are simply the fact that diffusion doesn't happen just locally with very small steps, but most of the time, of course, you have small steps, and from time to time you have long jumps that take you that take the particle to large distances. These are Levy flights, which are responsible for this heavy tail here that appears here. So just a word to say that this was observed. Similar physics was studied and observed in the case of the proton structure and nuclear structure in deep inelastic scattering, where the photon gamma star proton cross section also exhibits similar geometric scaling, where now the saturation scale is of course different nature here. It's related to the nonlinear effects due to the recombination of gluons inside the proton at high energy, small x. Nevertheless, it's similar feature, although the physics is different. So, as I said, this remarkable scaling extends to KTs that are much larger than the saturation scale, which describes the peak region. So this scaling would extend all the way to very large KTs. Of course, there's a boundary which is given by QS squared divided by the non-perturbative scale, which is related to the bimass. And the larger the QS, of course, the larger the window. And this is what I showed here. You see that the scaling extends to very large momenta here. And then here we fitted here the spectrum by the power law, which is the analytic solution, which is given by 4 minus. This is the deviation from the Coulomb scaling here, which is given by high order corrections, which is square root of alpha bar. So typically what you have is you have a heavier tail, somehow harder tail, as you can see here. And of course, you gain in order of magnitudes. And this is important. So the rare events which happen at large KT are enhanced due to quantum corrections, and this could have some repercussions in phenomenology. If you measure momentum broadening of jets, say in dijet events or gamma jet events, this could enhance the signal. And by focusing on the rare events here, we might even probe physics that happen around the QS scale because of this extended window. So the physics of scaling is not confined to the peak region, but extends to higher KTs. So this is the last plot and last slide, just to show you how this transverse momentum broadening evolves with time. So again, you see here the tree level. This is L. L is time. This is just the system size. So there is a sensitivity to system size due to the non-locality of quantum correction. So the median. So we took the median of transverse momentum squared because the average would be very sensitive to the tail and could even diverge. So this is typical to Levy distributions. The moments do not exist. What you can do is to capture the typical event, you can calculate the median. And by calculating the median, of course, you are measuring the saturation scale. So the transverse momentum squared is the saturation scale. And for the for tree level, again, it scales roughly like the length, well, his square root, depending if you measure, this is KT, so it has to be square root of T. But because of the Coulomb log, the exact tree level would have an additional logarithmic enhancement, which is mild. And here, because of the quantum corrections that would enhance the diffusion, you get an additional anomalous scaling here, which is 2 beta, beta being the square root of alpha bar. So for alpha, I think here it's 0.2, you get beta 1.18 here. And you see clearly how you have this divergence of the two curves and this typical super diffusive regime here. So this brings me to my summary. So jet physics in heavy ion collisions is a very rich topic. It's multidimensional, multi-scale probe of QCD dynamic, QGP, and the non-equilibrium dynamics of QCD. So here I just touch on 2 aspects that somehow kept me busy lately. So at weak coupling, you can work out things from first principles. And you can see the emergence of new phenomena, such as this inviscid turbulent energy transport that is local and is marginally sensitive to the physics of dissipation. So we can understand how energy is transported from the TV scale to the GeV scale just using recoupling techniques. And then, of course, we have the anomalous diffusion, color decoherence that leads to this color randomization of partons of jets when traversing the medium. And as I said, they can be studied from first principles using resummation techniques. Transverse momentum broadening, as I showed, is governed by superdiffusion, and this is quite remarkable compared to the leading order result, which exhibits standard diffusion. And in addition to this superdiffusion behavior, we have geometric scaling, which entails that the distribution is function only of a scaling variable, which is KT over a typical transverse scale, which is the saturation scale, and leads to this heavy tail, harder spectrum as compared to the leading order, which extends to a very large window in KTs all the way to QS squared over the divide mass. So outlooks is of course to these are phenomena that are studied from first principles, but ideally would like to be able to measure them in experiments, and this would require to develop high precision computations to investigate them at RHIC and the LHC. And for the anomalous diffusion, one of the processes that we would like to see is Diejet azimuthal correlation that is extensively studied. So it would be very, very interesting to see whether we could measure those kind of remarkable anomalous phenomena in experiment. Of course, jet substructure, Diejet asymmetry, and the list goes on. There are many, many observables that we may tackle and investigate to study those phenomena. And with this, thank you.
Oh, thank you very much for a nice presentation. Now we will have some time for questions. And the first question is Giorgio Terrieri.
Hi, thank you for a very nice talk. Just in the conclusion, you mentioned, maybe you mentioned it in the talk and it kind of went by me. You call this inviscid. Is this because it's not dissipative? It's a one-to-one between initial conditions and final states, or is there another reason? I just would like a clarification of this.
So inviscid meaning here means that during the cascading process, right? The cascading process is not sensitive to viscosity. So you could the cascade, because it's not sensitive, it doesn't depend on viscosity. You could very well set the viscosity equals to 0. It doesn't prevent the turbulent cascade to happen. So inviscid meaning that there's no sensitivity to viscosity until you hit the microscopic scale. Of course, you have viscosity at microscopic scale. You have dissipation.
But you're not dealing with sound waves. Ultimately, you're dealing with gluons, no?
Well, but this is general, right?
The jet is not emitting sound waves. It's emitting microscopic particles.
Yes, yes.
So viscosity is a sort of macro to micro diffusion, if you want. Here, this is a purely micro phenomenon.
Well, yeah, it's you have microscopic phenomena that will lead to microscopic emergent phenomena, right? So this turbulent cascade is microscopic phenomena, and this stage of the turbulent cascade doesn't depend on the dissipation that occurs at smaller scales.
Okay.
Yeah. So it's really physics that happens between the large scales where basically you are which is called the injection scale, where energy is injected, right? This is the largest scale, and then you have microscopic scales where energy is dissipated, the sink. But in between, the physics is completely independent of the viscosity. So really, this is how Kolmogorov derived his result. He didn't need the viscosity in his calculation.
No, okay, I understand. Just sort of, sorry, just as a sort of, in practice, sort of the configuration size of the jet and the fluid, if you take hydrodynamics, especially in small systems, seriously, are comparable. And you haven't really said what happens if a sound wave hits a fragmenting jet, right?
Well, the sound wave could also be triggered by the jet.
Yeah, of course.
Right, and this would happen at really low momenta, right? Really, this is the regime, the hydrodynamical regime. the regime I've been talking about is the regime which leaves really at high momentum, right? So the physics of the sound wave would certainly become important and relevant when you reach the thermal scale.
Okay. I mean, sound wave carries a lot of energy. It's a large wavelength, but it's a higher occupation number. But okay, fair enough. Thank you.
Yeah, I mean, this is something to think about, of course. These considerations here are focused on really the hard momenta of the jet, and any physics, and this is relevant, right? The question is how, this is the physics of back reaction.
Sure.
If you create a sound wave, how is this sound wave going to affect, you know, somehow the jet itself? This is a nonlinear effect that, of course, is assumed to be negligible in this description, but might very well be important. This yet to be.
Okay, thank you.
Okay, next question is Bernd Miller.
Oh, okay. I have a question.
Hey, Yacine, can you hear me?
Yes.
Yes, go ahead, Bernd.
Okay, very nice talk. Really enjoyed it.
Thank you.
I have one quick and one maybe a little lengthier question. The quick question is just going back one slide. I want to make sure the red line, is this really true that the power goes from T log T to T to the 3.36?
Yeah, yes. So this is of course very large media, right? You see, it's L100 Fermi. So we are looking at asymptotic scalings, where but the T log T is just the standard leading order, right? We get
Yeah,
T,
I know. Right.
And then here, this is simply the resummations which lead to the exponentiation of the time. So the log would turn into, it's like when you calculate, of course, in Parton distribution function, the next leading order would give you a log, and then the resummation of the logs will lead to the anomalous dimension, which is logs turns into powers, right? And
Yeah, I understand. The power seemed very large. That was.
Oh, the power is just a number which comes from the fact that you see you have square root of alpha s. So if alpha s is 0.2, then the square root of 0.2 is not so small. And this simply means that this description is valid to leading log, meaning that alpha s should be small enough so that you can neglect higher order corrections like next to leading log. But obviously you cannot trust those numbers if alpha s is too large, right?
Yeah, I understand.
Yeah, so these are just numbers. Just take them as you know, nothing really somehow set on stone. But this is qualitative. And if you want to do quantitative predictions, I think you need to control theory uncertainties by computing next to leading log and put a band there. And then that would be that we have a more accurate somehow description. Yeah.
Okay, so my physics question.
Sorry, Bernd.
My physics question is a little different. So you talked about the anomalous behavior as a function of the jet axis, the jet KT, right? Mm-hmm. What about the jet profile, the intrinsic transverse momentum inside the jet? Have you looked at that also?
No. Yeah. So here I really focused on the momentum broadening of a single parton, a single color charge. Yeah. So the how a jet as a multi-partonic system, is that the question? How a jet as a multi-partonic system would suffer momentum broadening? I haven't looked at that yet. It's a more complicated problem, but certainly this would appear there would modify the broadening of the jet as a whole.
Yeah, it would be interesting to see. I mean, you have the scaling regime in X, right?
Yeah.
With the energy flow, it would be interesting to see whether there's similar scaling regime in the intrinsic KT.
Yes, I would say this. I think there is a simple somehow case study here. If you take a very narrow jet, right, very narrow, so this jet would not be resolved by the plasma. So it would see only a single color charge. In this case, the internal structure of the jet wouldn't matter for momentum broadening, right? Because the jet is so collimated, you have color somehow transparency. It's only the part, the leading color charge which would matter, and all of this discussion would still hold because you can only the jet substructure wouldn't be modified, so to speak. Of course, if you open up the jet axis and then the medium starts seeing color charges inside the jet, then you start really invoking more processes that relates to energy loss, more complicated energy loss, more complicated momentum broadening. And in real life, an experiment will have to do this. So the question is how to go from this somehow idealization, theoretical idealization, to really experiment. And I think that's the next step, I would say. Yeah.
Okay, thanks.
Okay, next question is from Graziano Mileto.
Okay, thank you for your nice report and exposure. On slide 25, it is written that the energy spectrum of the gluons is suppressed due to the effects of the coherence in the medium. Could you clarify what the coherence effects can be? That is, in other words, which experimental evidences have features of coherence in medium?
Right, so there are many coherence effects, but here, this is related to the Landau-Parmelee-Schuck-Migdal effect. So the gluon radiation here, it takes a certain time to decouple from somehow to go on shell. So the radiation happens after a certain time, right? So it doesn't happen instantaneously. So it takes a certain time. This is given by this. So it's non-local, so to speak. During that time, which is a quantum mechanical process, it's not classical, multiple scatterings could happen. So those scatterings, so the gluon doesn't see multiple scatterings. The gluon will feel only one scattering. So there's one effective scattering that will trigger the radiation, although there are many scatterings. So they act coherently to produce that gluon. So here, for instance, you have 3, they act coherently as a single gluon to produce them. Now, why do you have a suppression? Well, say you have a certain number of scattering centers, say you have 10. If each radiation is produced by 3, right? So then the effective number of scattering centers is not 10, but it's going to be lower. It's roughly 3, right? So because you have less scattering centers because of this non-local radiation process, then the spectrum is suppressed. And this is what you see here. So the spectrum is suppressed compared to the standard incoherent radiation. Incoherent radiation meaning simply you multiply the number of scattering centers, right, times the radiation alpha s. That's it. It's constant. If you didn't have coherence, you would have just a flat spectrum here. But it's suppressed simply because the larger the frequency, the longer the formation time. So the larger the frequency, the longer the formation time, and the smaller the number of effective scattering centers.
Okay, thank you, I understand.
Any other questions from the audience? I have some question that I want to clarify. When you were talking about the turbulent energy loss, essentially that scaling regime or whatever you call it, you were saying that essentially it's not sensitive to the viscous effects, but it is sensitive to the Q hat. Is that a correct statement?
Yes.
Did I get it right? So it's sort of two-sided question. First of all, if that is the case, it means that we have some intermediate region of jets, which will be essentially telling us the information about the Q hat in the observable data. Is that correct? And which data do you want to use to extract the Q hat from there? That's one part of the question. And the other part of the question, Q hat is essentially a dissipative process. So it's not exactly cascading kind of process. And in a way, it means that there is dissipation. And how is that different from viscosity?
Yes, it is. Yeah, good question. Of course, you're right. So if you factor out Q hat, there are no dissipation processes. It's just a cascading process. Somehow it's an effective description, so to speak. So Q hat is completely included into this branching rate, right? Once it's done, that's the only, say, medium property that we need to care about during this cascading process. And then, in addition, there are no other. You could imagine a scenario where, say, the physics around the thermal scale, where you have nonlinear effects and detailed balance, could then affect the hard scales through additional, say, transport coefficients, a large number of them, right? So the fact that if you have a large enough window, you can describe this cascading process having only one or two transport coefficients. That's the message. So
Q hat is the only one that matters.
Yes.
In this regime.
So this is I think this is maybe the explicit picture. So here in thermalization, in this regime where you have thermalization, you need really to have detailed balance. You need to know the exact mechanisms of thermalizations here, right? And in fact, Q hat is a number that is not sensitive to those details. In fact, the jet is just a small fluctuation in the perturbation on top of a large medium. So Q hat is not sensitive to how the jet would thermalize. So the Q hat that is entering the turbulence cascade here is the Q hat of the bulk. All right. So if you know that Q hat, if you studied, say, you know it from first principles. In principle, we should be able to describe the blue regime and the orange regime, the turbulence and the jet, without knowing exactly the details here of the thermalization. You can even ignore it because you see here, these two stages are exactly the ones that we obtain here, here, without even caring about detailed balance. There is no detailed balance here. It's as if energy flows all the way to zero frequency. So if you don't have detailed balance, it will just continue flowing and flowing and flowing forever, in fact. So the only quantity you need to know is Q hat. But of course, it's a dissipative effect. I said if you factor out Q hat, that's pretty much it.
Well, but what's about the observational footprint of this Q hat? Do we?
Yes.
How do we? Yeah. Go ahead.
Yeah. Sorry for that. So now we know. Say here, we have exposed how a single parton loses energy, right? So we know that a single parton would go through this cascade here, and this, in principle, we can model. We can calculate either analytically. It's tedious, or you can either simulate your cascade. And then, for instance, you can measure the inclusive jet spectrum, right? So if you measure a jet, right, and study the inclusive jet spectrum, you can, of course, you have to some extent fit Q hat to the data, right? That's how you're going to extract the Q hat. Of course, here again, a jet is multi-partonic system. You have to solve the problem of how multi-partons lose energy. And then after you solve this problem of how multiple partons lose energy, which means having this process, turbulent cascade for each parton in the jet. And this in fact, I have slides here, which I can maybe show you. It's a nonlinear effect. So basically this, you have energy loss of multiple partons, and then the multiple partons this energy loss would obey a nonlinear equation. So this equation is completely vacuum physics. I don't want to go into the details. Q hat enters the initial condition. So the initial condition, which is the energy loss of a single parton, is sensitive to Q hat through this frequency omega s. So this is to say that if you solve the problem of single parton, right, which is now a function, you get a function, right, of Q hat. You have an analytic function of Q hat, like here. It's an exponential minus square root. It's omega s is Q hat times length of the medium. Now you have an analytic formula, which you plug in as an initial condition for the vacuum evolution. This is perturbative QCD. It's similar to DGLAB. Then you obtain a jet spectrum, which now you can use to extract Q hat from the data, as we did here. So this is what we did. So this is the RAA for different centralities, and you see jet PT here, from 100 to 1 TeV, and then Q hat here is fitted through the medium coupling constant here. So the band here is for Gmad, which is the coupling constant that enters Q hat, the leading order Q hat, which is given between 2.2 and 2.3.
So the bottom line is you are fitting the high energy jets, as I see from the scale, and essentially from that fit, you extract Q hat.
Yes.
Okay.
Yeah. But you could, but the point coming back to, you could be sensitive to more details of the medium, even at the high. So the fact that you end up being sensitive to just a few transport coefficients, that's first remarkable, and that's a blessing because we are able to have a clean, relatively clean probe, so to speak.
Right. Okay, thanks. I get it. Now, sort of maybe a follow-up and maybe sort of another question in a way about this super diffusion. Again, if my understanding is correct, essentially it's the high energy jets that will be sensitive to it. And it seems like, if I interpreted it right, it seems like the actual suppression seems different than without this super diffusion. And does it mean that in the extraction of Q hat, if you were to consider naive theory without this super diffusion, you would extract a very different value of Q hat than if you include it? So does it essentially introduce additional uncertainty in the extraction of the properties from the data?
Right. So yes, there are two uncertainties here, two possible differences. So the first difference is just some constant prefactor. Suppose this effect is just enhancing Q hat, right? Suppose the effect is just sorry. So let me see here if I find the. Suppose you just enhance Q hat just by, then the fit would, what you would fit in fact to the data is not exactly the, say, the temperature scale, right? If your goal is to fit the temperature using the leading order, then you're actually not fitting the temperature scale, you're fitting there's a K factor which comes from high orders, right? So if you usually, when you compute high orders, this would sometimes high orders are very important, and they are not really related to the physics of the plasma, but rather to the dynamics of vacuum. And you need to know how to calculate that. And you're right, if this effect, if you have a large medium, if you have a large phase space, then you should worry about that if you want to have an accurate extraction of Q hat. Now that's the first thing. The second thing, so this is, if you want accurate, you can still extract Q hat with a certain uncertainty, which would be more or less large, right? But it's still valuable information. But if you want to have it be more accurate, you need to worry about this. Now, the second thing is the scaling. It's not only about the factor. You have an anomalous scaling. And if you have an anomalous scaling, then you would have, say, if you scan the centrality or if you scan system size, if the system size changes, right, you could fit for small systems, relatively small system. This description is valid only for large systems, okay? But let's say, relative, for different system sizes, then if the scaling is different, as you see here, then it's not just the K factor to fit, right? So you have to worry about also how this the Q hat depends on the system size.
Okay, good. I think we have no more questions. I don't see anybody else. So using this opportunity, thank you again, Yacine, for a very nice presentation. And with that, we will be wrapping it up.
Thank you.